Welcome to a discussion of satellite systems. And the satellite system we want to talk about in this module will be the geostationary Earth orbit type of application. My name is David Zimney, and I'll be your instructor in this module. Remember, if you have questions, be sure to use the question comment box on GoGo. Let's get started. In this module, we're going to talk about, introduce the concept of satellite communications and the technology associated with it, and then focus on geo implementations, which comprise the largest amount for actual telecommunications use of satellite technology. So, what do we have in the way of satellite systems? In satellite systems, we have three major parts: the satellite, or the constellation of satellites, depending on how sophisticated a system we have. And these are obviously orbiting in some part of the outer space around the surface of the Earth, moving at very high speeds. We have a ground control system, or ground control station, and then one or many, a multitude of Earth stations. So this is what we'll see, is a group of satellites that can be communicated with from a ground control station, and then the satellites relaying information, the satellites relaying information down to the Earth stations. Let's talk about different satellite types. Satellites are generally, in terms of the types, are classified as low Earth orbit. A low Earth orbit satellite is in an orbit just a few hundred miles above the surface of the Earth. Have to be a few hundred miles above the surface of the Earth to be safely out of the remnants of the Earth's atmosphere. As a result, the satellites are in view from a point on the surface of the Earth only a few minutes during a single orbit. A middle or medium Earth orbit location is an orbital altitude a few thousand miles above the surface of the Earth, and by extending the altitude of the orbit, then we are also extending the satellite visibility time from just a few minutes up to potentially a few hours. And this is assuming that we're looking at it from a fixed point on the surface of the Earth. A further classification is a specialized circular orbit around the Earth, and that is the geostationary Earth orbit of 22,300 miles above the surface of the Earth at the equator. And this is an equatorial orbit, and it has a satellite that appears to be stationary in the sky. So this is a specific orbit that at the equator, an orbit moving in the direction of the rotation of the surface of the Earth, gives what appears to be no movement between the surface, any point on the surface of the Earth and the satellite. So, then another specialized type of orbit that can have some advantage for communications is a highly elliptical Earth orbit, and we'll cite some examples of what these are in upcoming slides. Okay, so here we show the geostationary, and obviously we can't get all of these to scale to fit on a single page. The geostationary Earth orbit at 20,000 plus miles compared with a middle Earth orbit and the highly elliptical orbit. But I think you get an idea of the time. What happens in these orbits, especially elliptical orbits, you have a slower orbital velocity as you move away from the object around which you're orbiting. So we have in an elliptical orbit a very fast pass time when the satellite is close to the Earth, and then a much slower drifting time as it's in its point furthest from the Earth. So these could have specialized applications for observation for phenomena on the surface of the Earth, and then long drift times to download the information that has been recorded during an observation. So, what kind of coverage do we get? Obviously, with everything but geostationary Earth orbit, then we have possibilities of just all different types of coverage. However, for communications, what we like is a large area of coverage. So with 3 geostationary satellites, we can cover all but the polar regions of the Earth. And we have coverage, I think, up to around 65 degrees, both northern and southern latitudes, which is, in terms of providing communications access to human locations, then these are fairly good. We use specialized orbits for communications with polar research stations and things like that. So that means geostationary satellites are ideal, or the optimum satellite configuration for most business applications. And a nice advantage is that we don't have to do any tracking of the satellite as it moves across the sky, and there is no Doppler shift. And many type of encoding methods are Doppler sensitive, so we don't have that in geostationary satellites. However, there's nothing free, and that means that in our design here we have everything going for us, except that due to the very high orbital position, then there is a substantial propagation delay from Earth station to the satellite and from satellite back to another Earth station. So the total Earth coverage requires the use of non-geostationary type systems. If it is important to have total Earth coverage, such as in a system like Global Positioning System, then obviously these cannot be based on geostationary approach. So that means that control and so forth would have to deal with tracking, and we have limited coverage time for a single satellite. That means that we would have to have an expanded constellation of satellites to be fully functional. And the applications that we used in coding methods will have to deal with the Doppler effects. And, since there are multitudes of systems in operation, obviously these issues have been resolved. Let's take a look at some of the uses for satellite communications. Namely, the primary one is for telecommunications. In essence, a satellite is just a radio relay station in orbit above the Earth, where a signal from the Earth is received. It is converted to a new frequency for downlinking, as amplified, and then retransmitted back to the Earth. So it's just a relay device, a very expensive, very sophisticated relay device nonetheless. Other types of satellites, in addition to communications, weather observation satellites, and Earth observation satellites, and one that we're all familiar with are navigation satellites, such as the Global Positioning System. So, what are some of the benefits? Universally available. They're fairly reliable, a very reliable technology. Satellites were originally projected to have a life cycle of around 8 years, and many of the Intelsats have operated well into decade plus operational cycles. The bandwidth supported as a result can give us high-speed, fast communications, but don't forget that depending on the orbital position, there may be some high latency, long delay due to the long paths between satellite and the Earth. And we get seamless type of coverage here. We can do this all throughout our zone. At any place on the surface of Earth we want coverage. And it's scalable in terms of the number of interconnections we need to make and the bandwidth of those connections. So as a result, we have a very flexible type of technology if we can deal with delay issues associated with orbital position. So let's take a look at some of the frequency ranges that are used in satellites. And the game we have to play is that since we have to talk to the satellite, we want to use frequency ranges that minimally affect the radio signal to and from the satellite. So VHF ranges are more apt to interact with the Earth's atmosphere, so they're not ideal. Very high frequencies, millimeter wave type of technologies that you see listed there, sound good but have a phenomenally high path loss, so those don't make any sense either, except in certain type of applications. But transmitting to and from the surface of the Earth, we don't use those. If you look at all of the bad things that can happen to a signal going from the Earth's surface to the satellite, the effects are minimal in the 4 to 6 gigahertz range. So it's no wonder that the first reliable communication satellites were built around C-band technology. So the footprint is the coverage area on the Earth as set up by the antenna systems on board the satellites. And this used to be a fairly lucrative business for the satellite designers or designers, is to be able to customize the beam shapes before the satellite was launched. We wanted to minimize having too much electronics on board for on-the-fly type of configurations. So this was done before the satellites were launched, and wanted to ensure that we had good signal strengths on land masses. Now, there are satellites designed for communications in between the land masses, but most of the telecom is from one land mass, one continent to another, or within a continent. So antenna beams are carefully designed to cover the regions that we want. The global coverage, we can get roughly 1/3 of the surface of the Earth, though, with one bird, and that means we can go for hemispherical coverage, almost 1/6 of the Earth's surface with one particular satellite. So these are the phenomenally large potential areas for coverage, and we can get zone coverage by covering land masses, or spot coverages for covering specific regions, or even cities or groups of cities on the surface of the Earth. So here's a block diagram of a satellite that give you a feel for the complexity and hence the cost associated with a satellite. Have to have some type of propulsion system to ensure that the satellite stays within its required orbital positions. Have to have some type of communications for ensuring that the vital systems on board the craft are functioning properly, namely telemetry for dealing with altitude and attitude control here, fuel, battery monitoring, power monitoring, and thermal systems to ensure that there is sufficient cooling and protection against exposure to, it's exposed to the thermal radiation all the time, so we do have to have a lot of reflective protection, and sensitive electronics needs to be buried down inside the satellite. Well, other issues here, functioning of the high power system in the receivers, down converters, frequency translators to go from the uplink frequency to a downlink frequency, and then the high power amplifiers themselves. And many of the birds still use a vacuum tube or traveling wave tube type technology, because if there's any physical damage to it, unless it's a huge physical damage, then loss of vacuum and so forth doesn't affect its operation. So very complex and very expensive, but also very reliable. Okay, what do we see in a two-way systems? Earth stations receive downlink and transmit to a station on the uplink. Satellite systems can support a wide variety of data, and we're talking primarily about geostationary systems here. Because there's no Doppler shift, they're in a constant position, and we can get good predictable radio channels established, and very long delay but very low jitter seen between an Earth station and a satellite. So we get a good support of any type of business service, voice, video, or data. Some example: a very small aperture terminal, a VSAT in geostationary Earth orbit, such as HughesNet, DirectWay, Globalstar, Iridium in a low Earth orbit. And we'll go into a little more detail of these later. So different orbital positions, but still solid communications. What type of topologies exist in satellites? We have a star type technology from a hub talking to the satellite, broadcasting to a group of hubs. A mesh type of technology where we interlink through the satellite. Most video distribution is a star type technology. We have a uplink on one bird that then relays the information to many Earth stations on the ground. Or we'll uplink to one bird and go to other distribution systems that distribute the programming through a terrestrial method. Or a mesh technology could, the disadvantage here is that operating in an interactive way here is there's roughly a 250 millisecond delay, so the long delay does affect the overall throughput seen in this type of application. But both topologies are possible. What a lot of us have on Earth for our television programming is a TVRO, receive-only type of installation. Earth stations receive signals on a downlink. Uplink comes from a control system, and some examples are DirecTV, XM, and GPS. So both geostationary Earth orbit, middle Earth orbit, and high Earth orbit. And notice an XM is a geo installation. Sirius is a highly elliptical orbit. We'll see that in a minute. So the uses: television broadcast, weather, navigation services as well. Most common to communications systems is geostationary Earth orbit due to the fact of the wide potential coverage area, much more extensive. I can do point to multipoint distribution with a geostationary satellite and cover many, cost effectively cover many more users than with a terrestrial network. Communications uses fixed high gain antennas, so we can take advantage of the ability to improve communications with the antenna systems. We don't have to use any fancy modulation and coding methods. So you've got to point the satellite dish once and in the right direction. And we see how easy it is to install the TVRO stuff for dish network and stuff like that. So it's easy to do. Now, big antennas are much more challenging to orient. So geostationary Earth satellites are a reliable technology and 10 plus years for satellite operation. So how many of them are there? There are dozens and dozens and dozens in geostationary orbit. And I know you can't see all of this stuff, and the operational birds in the constellation change continually, but the important thing is it's obviously a reliable technology and something worth investigating for communications needs, especially if you have many locations spread out over a wide geographical area. So it's crowded. The spacing is around 2 degrees. Back in the 80s it was 5 degrees. So 2 degrees doesn't mean you're going to bump into anything. So let's take a look at some of the applications here in Inmarsat, and you can freeze this frame and look at it in detail, but here is voice and data type services. Not very high speed. This is pricey, but this is a system that's been around dozens of years now, and well, not multiple dozens, but a long time. And the key thing is that it's based on a satellite technology. So Intelsat has been in business now, I guess, since not long. Well, one of the pioneers in bringing together international telecom based on satellite communications using geostationary satellites. So you can see their birds are scattered around the world to provide interlinking of information from countries all over the world. So Intelsat I was called Early Bird. It was the first one, launched in 1965, supported a whopping 240 voice channels. That meant you could have 120 duplex conversations. And Intelsat IX is kind of a mid-generation now, still in operation, launched in 2003, supports 112,000 voice channels, and we put those there just for to show how the electronics has expanded. Let's take a look at VSATs, very small aperture terminal, and that's talking about what? The antenna size, the antenna terminal on the surface of the Earth, in the Earth station. So VSATs generally used with geostationary satellite systems because they can't be used with something else that would require antenna movement. The idea is to have an inexpensive antenna terminal involved. So high power from a satellite and high frequency operation. KU band is in 1114. It's actually around 12 to 18 gigahertz, depending on which chart you're using. The KU band as defined for satellite operation is around 11 and 14 gigahertz. So moving up from the 4 to 6 gigahertz to the 11 to 14 gigahertz introduced higher path loss, but what we're able to do is reduce the size of the antenna substantially, and this then made it more cost effective for people to install these type of systems for their businesses. So older TVRO, television receive-only systems, used a 2 to 3 meter diameter antenna anywhere from around 6 to 9 feet. Not too attractive in most residential locations. Difficult to align because of the perhaps a higher gain. Current systems can use antennas anywhere from around a half to 1 meter, depending on whether you're trying just for television receive only or for duplex operation uplinking. So you don't have a problem with the reduced aperture size. You actually have a slightly lower gain, which means wider beam shape and easier to align the antenna, giving adequate signal quality for most low speed. It's great for television, may not be sufficient for data. High speed uplink is not available with these antenna types. So, some of the VSAT technologies, I can use this to provide what looks like a hub location and relay information in between. A lot of businesses use this, especially multinational locations can use a VSAT type system to let the headquarters facility bring important strategic messages to all of the remote units scattered around the world. So a lot of businesses will relay time-sensitive information via a VSAT type network. Stock market news, training, continuing education from a distance. In a broadcast environment, these are a little more successful than they are when they are duplex because of the long propagation delay. Financial information, introduction of new products, very important for Salesforce to get information uploaded. Updating market-related materials, and one of the biggest is distribution of video or television programs. It's the biggest market for not only VSATs but for geostationary satellite operation. Music distribution, advertising. So, think about it. Could your organization benefit from a VSAT, or you may very well already be using VSAT technology. Disadvantages: the installation. Satellite network can be installed in a matter of weeks, since there are not countless miles of cable to deal with. Geography, unless you're in a very mountainous area or in the polar regions, then you can always see a satellite, and you have to have line of sight operation here. And bandwidth, well, you can get the bigger the antenna that you have, then is the bigger the pipe you can have for dealing with your applications. Two-way, interactive computer transactions, internet access, video conferencing. These are all possibilities, but you notice the ones that really do the best here are fairly low bandwidth type of stuff. Especially if you're dealing with a small antenna, you're going to be bandwidth limited, and that means the application will have to be bandwidth limited as well. So bank transactions, reservation systems can be very effectively tied together with a VSAT network. So, other things, emergency services. The FEMA folks use VSAT systems whenever they need to be put in place a comm system after a natural disaster. So, providing voice communications, email, medical data transfer, sales monitoring, a variety of things. So, here's a service provider, HughesNet or DirectWay, satellite-based internet access. It's about 10 times faster than dial-up. Now, this is important because if you can get DSL or other wired services like cable access, then the speed here is still much, much, much lower than what these services, the wired services, would give you. But it's faster than a wired dial-up, assuming that you can only get around 40 or 50 kilobit per second on dial-up. Subscription fee is reasonable, and remember that this is great because it does not require any access to a telephone line unless you are dealing with uplinking. Uplinking may require access to a separate terrestrial line to access a hub through a terrestrial connection. But you must have an unobstructed view of the southern hemisphere. OmniTRACS is another application here, real-time vehicle tracking, GPS or Qualcomm proprietary positioning system, and national coverage. Been in operation a number of years and may offer some features that are important to you, especially if vehicles are a large part of your business. So, OmniTRACS is designed to integrate accurate real-time tracking information. Also to include dispatch services, route planning, accounts receivable, accounts payable, driver hours. You can see that this for very, very vital service or appropriate service to the trucking industry. to handle a lot of business applications while a particular unit is on the road. So we're showing this here and looking at communications with the satellite, have a network management center, and then we're able to communicate with our vehicles out in the field. So, and put this insert here just so if you want to see what it looks like on a vehicle when you're passing or out on the road in the U.S. looking at on the interstate highway system, and you see this type of dome on the upper portion of the cab of a truck, right in here, then this is your OmniTRACS type of system. And slightly different terminal. All right, XM radio. If you have it, then it's a very pleasant way to have unobstructed communications. In the L-band here, based on 2 geostationary satellite positions, and this is to make sure that you don't have a sun outage problem. Satellite orbits are geostationary, feature over 200 audio channels based on a 128 kilobit data stream, and that means we can get very high quality. There are some terrestrial impeders involved. Well, do you have any questions? If you do, use the question comment box and let us know. Thanks for joining us. See you soon.